Hi, my name is Kendra. I'm a student here for the summer. I'm working with Kavya and Zachary in the Robotic Caregiving and Human Interaction Lab. And my project is Reversibility-Aware Optimization for Cloth Manipulation. So some background work that has been done in the lab is called robust body exposure, or ROBE for short. And it looks at uncovering targeted areas of the body using a robot. For example, if you wanted to uncover the left leg, you would lift the blanket up from this corner and drag it here. Some of the motivations behind this work is it will ease the workload of caregivers and nurses, and it also additionally gives people with disabilities more autonomy and independence. If they wanted to adjust the blanket themselves, they no longer have to rely on someone to do it for them. So the way that ROBE works is it uses a graph neural network to learn the dynamics of the cloth and then predict the displacement after an action is taken. So the first step is so you have your blanket and you turn it into a point cloud, which then becomes a graph. So all of these particles become the vertices, and then there's edges connecting them. And the next step is you plug that graph into your dynamics model, so your GNN, along with a proposed action to predict the change in the cloth after the action is taken. So the action is a four-dimensional vector consisting of a grasp location, so where you're going to first pick up your cloth, and a release location where you're going to release it. So you plug both of those things into your dynamics model to get the final cloth state. So you have your initial cloth state plus your displacement equals the final cloth state. Since we're trying to uncover certain areas of the body, for example, like the arm or the leg, it's important to evaluate how well the action actually uncovered the leg. So we use an objective function to do that. And the way that we test if a point, like if the body is uncovered or not, is we generate points along the body to match the pose. So for this, you can see like if a certain point is within a distance, a certain threshold distance to a point on the cloth, then it would count as covered. And if it's not, it's uncovered. So through this method, we can test like if the arm is uncovered or if the leg is uncovered. And if it is, we just take that action and then we move on to our uncovered state. And if it's not, we run it through this optimizer to resample another action to try and uncover the person in a better way. So where our work comes in is we are trying to now recover the person back up. So ROBE has looked at how do you uncover a person and now we want to recover them. So if you uncover the right arm, this is all ROBE, but this is where our work comes in, is how do you cover them back up? So it's not as simple as it looks, or you can just like take your action and then just reverse it, which is the naive reversal, because some cloth states are irreversible. They get like self-occluded or folded and you can't cover the person all the way. So for example, we ran some tests in our lab that looked at like uncovering like the leg on the mannequin. And while this would be perfectly fine in the ROBE context where it uncovers the leg, well, if you try to recover it, it ends up leaving this portion uncovered. And we tested another action trying to uncover the entire torso. So this accomplishes it fine, but then when you try to recover it, you have these like dovetail symmetrical folds that when you just do the naive reversing action, it leaves like all of this uncovered. So it's not as simple as it looks. And again, we are constrained to reversing and recovering the person in just one action. So although it might be possible to have to recover the person like multiple actions, we are constrained to only doing it in one action. And then what creates a reversible cloth state? We also tested this in lab to try and get some ideas about it. And we found that pulling from the edges of the bed tends to be better than pulling from the middle. Like if you pull from the middle of the cloth here, you can imagine like it's going to get very self-occluded and kind of folded in on itself. Whereas if you pull from the edges, it creates like a nice diagonal fold, and it's easy to reverse. Like in this case, we were just testing that naive recovering action, and it was able to recover the person entirely. We also found that maintaining a lower distance to the body when you're doing the uncovering action tends to create less self-occlusions. And then in the other spectrum, when you are recovering the person, if you lift the cloth up higher, it is better at recovering because it can like unfurl larger folds. So these are just observations that we found in the real world of what defines an irreversible and irreversible cloth state. So because there are like irreversible cloth states, we want to reason about preventing them. And there's this paper by Google that came out, Reversibility-Aware reinforcement learning, that looks at how do you prevent agents from entering into irreversible states. And I think this is a really important problem in robotics, because if a robot enters into an irreversible state, it's going to need like a human to come and help reset the workspace of the robot. And I think there's like a joint problem of learning how to recover from actions, but this is more, or learning how to recover from failures, but this is looking at more like how do you prevent the failures in the first place? And how do you never enter into a state you cannot get out of? So we are using this concept in our work, which is like, how do you uncover the cloth in such a way that you know that the resulting cloth state will be reversible? And I have this diagram here that shows you take an action from state A to state B. This is a probability that you can reverse it. Like, what is the probability that state B can then go back to state A using another action? So this is what we have been exploring, is how do we encode the notion of reversibility into our uncovering action optimization. So just as a baseline, we're testing how does it perform if the uncovering and recovering models are optimized separately. So that would mean that the uncovering has no notion of whether the state it's about to produce is reversible or not. So this is just like a control. And then we came up with another approach, the semi-coupled approach, which includes adding, like explicitly adding terms into our objective function to create reversible states. So these are terms that we developed based on our observations in the real world, like pulling from the edges and like not creating these two symmetric folds that end up leaving a portion of the body uncovered when you're trying to recover. So again, like these are terms that we explicitly added. So we're injecting our own biases into thinking objective function of what we think will be the best way to create reversible states. And then we came up with another approach, the fully coupled model, which is instead of like us explicitly telling the model how to create irreversible states, we are going to let the way that the recovering model performs, so its objective functions result, be fed back in as feedback to optimize the uncovering model. And it's kind of like if you think of like a GAN, where both models are like one model is affecting the other. This is what it was inspired by, is the GAN training regime. So I'll go into more detail of these now. So this is the one where they're both optimized independently. So the uncovering model has no idea of the state it's about to produce, and the recovering model is just left to deal with whether the state is reversible or not. So this is our baseline, and I'll go over the objective functions now. So this uncovering objective function we are using from our prior work on robe, which is this uncovering. So robe is its goal is to uncover certain target limbs, like uncover the leg or the arm. So if it uncovers all the points on like the leg properly, it'll get rewarded for each point that it does uncover. If it uncovers non-target points, meaning if it's trying to uncover the leg and it uncovers the arm, it will be penalized for that. It's also penalized for covering the head, because just in general, like humans don't want their head to be covered when they're lying in bed. So if it happens to do that during its uncovering, it will be penalized. And it's also penalized for excessively long penalties. So for example, like taking an action from one diagonal, from like a diagonal of one corner of the bed to like an opposite corner would be a long action, and it'll get penalized for that. And again, this is straight from Robe. And then we developed our own, for our work, we developed our own recovering objective function. So if it can recover all of the uncovered points, so like if the leg is uncovered and it recovers it, it gets a reward for each point that it recovers. And similarly, if the target limb was the leg and the uncovering model uncovered it, but it also and only the leg is uncovered and everything else is covered. When the recovering action comes in, if it uncovers like the arm in the process, it'll get penalized for that. So it's like uncovering points that were never supposed to be uncovered in the first place. And then it's also penalized for recovering the head during the recovering process. So again, these are independent optimization. This is just optimized to produce like the best uncovering action to uncover the target limb, and this is just left to deal with like whether it's reversible or irreversible. So we have preliminary results. These are F-scores for optimizing the uncovering and recovering separately. As you can see, like they're not great. So it proves our theory that we need to have like some notion of reversibility awareness in our uncovering action because the independent optimization is not sufficient. So we developed these other two approaches, semi-coupled. This is the one where we're like explicitly injecting our biases into the objective function. So it's not being directly optimized yet, but it is, the objective function is reversibility aware, and it's optimized to produce like what we think are more reversible states from what we observed in the real world. And the way that it works is we use the same three terms from the decoupled baseline approach, and we get rid of this term for excessively long penalties because we found that excessively long actions, we found that longer actions tended to create more reversible states. So we axed that term, and we also add a term for grasping far from edges penalty. So when we were testing it in the lab, we found that when you grasp like along the edge of the bed, it tends to create like more reversible states because you don't have this buildup of occlusion in the middle. So we added this term onto it. And then we use the same three terms for recovering. And we also add this term for derivation from ideal action towards corner penalty. So it's a very long term, but and I'll go over that in the next slide. But again, this is like us telling or like injecting into the model like what we think will create more reversible states. So it's like reversibility-aware objective function. So derivation from ideal action towards corner penalty. This is like an idea used in the bed making paper by Seda to like make up a bed. And they found that the way that they were formulating their problem is the best way to like make a bed is to pull towards the nearest uncovered corner. So we thought that that would be a really good approach to perform recovering is you just you like try and find an edge on the cloth and then you pull towards the nearest uncovered corner. And I think it's interesting to think about that perhaps all cloth states could potentially be recovered in just 4 actions if you pull towards the near like every single corner that's uncovered. I think that's like an interesting idea to think about, but we use this idea from their paper. So like if you pull towards this corner, it'll recover. And if you pull towards this one, it should recover. And again, this, it does depend on like the states that are created. So that's why you need to have like this penalty that penalizes it from grasping in the middle of the cloth. So it's like, it's a joint problem. And then we developed one more approach, the fully coupled approach, where the uncovering model is directly optimized by the joint cost of uncovering and recovering. So this is similar to like, it's like inspired by GANs where like the discriminator will affect the generator. So in this case, like however well the recovering model performs, the uncovering model will be penalized for that. And the idea is like, well, the recovering model is only going to perform as best as the uncovering model can produce reversible states. So that's why we're doing the joint cost. Yeah, and so the fully coupled, so the objective functions for this model, we do the same 4 terms from the semi-coupled approach. So we get rid of the excessively long actions penalty, and then we just add on our recovering objective function to this. And we use the same 3 terms for as the decoupled approach. So the idea is like we are not telling the model like what produces the best reversible state. So we want the model to figure out like how to produce reversible states by being optimized like directly by how the recovering model does. So like again, it's just sorry, it's fed back in. And that is all we again we had a lot of infrastructure to set up to be able to do the recovering actions. So we've only gotten preliminary results for the baseline models. We are going to continue our work into the next semester to test the semi-coupled and fully coupled and see how they perform. So we don't yet have results for these, but we have hope that they're going to perform better than the decoupled and independent optimization has performed. So some interesting discussion questions that we've thought of is, should we base the fully coupled objective function on what the uncovering model did or like what it should have done? So the idea is that if the uncovering model has like tried to uncover, target limb is the leg, and then it's accidentally uncovered the arm in the process. And then the recovering model comes in and covers up both the arm and the leg. It'll get rewarded for something that it shouldn't have had to do in the first place. So we've been thinking about like, should we just feed in the state of what it should have been or what it actually did? And we're still in the process of discussing this. Another thing that we've thought of is like what other tasks could use this reversibility-aware optimization. So in tasks where you have to reason about the reversibility of a state, and you perhaps don't know what will create the reversible state. For example, like in the semi-coupled approach, we were able to observe and add in terms to the objective function to create more reversible states. But in problems where you can't do that, perhaps the fully coupled approach could you could use that, where the model is just like they're learning from each other on how to create more reversible states. So we've just been thinking about like other tasks that could potentially use that. Yeah, and I just want to thank the RISC program, Amazon for sponsoring me. Kagi is under this fellowship grant. And I just want to thank everyone involved in the RISC program because it was like a really great time. It was one of the best summers of my life, and I learned a lot of stuff. And so thank you so much for doing this. And if you have any questions, you can email me. My email is klg60@m2mail.mtsu.edu. I probably should have put it on here. I will put it on the poster. Okay, thank you.